Today on Zenodilodon, I'm in for repair in Fl-1064-10WB, which is manufactured by Endurance Lasers and is a 10-watt, 1064 nanometer laser designed for doing things like engraving on aluminum. So the client said that this laser had been connected to the power supply incorrectly. So I'm going to open up the driver and we can take a look at some of the issues on the inside and do some simple tests. Right off the bat, there's an immediate problem, and we can see that there's these 6 chips that look like they're all blown up. Now, I'm not going to get into what those are immediately, but let's go ahead and do some basic tests with the multimeter. Let's see if we can figure out what is good and what is bad. Now, I've already done some tests before, so that explains why the fan wires are disconnected. First thing we can do, right off the bat, see what the continuity is between the positive and minus that goes to the power supply this normally connects to. That is pretty much a dead short. Let's go to the pump laser diode, which is this little block right here. And that's fed with this pair of red and black wires right here. So let's see what's across that. Now, we're going to see 2 numbers, and that's because we're going to be reading the reverse protection diode or the diode that's in the regulating MOSFET, and then we're going to be reading the voltage drop that the actual junction of the laser diode gives us. So first, let's test the correct way. So positive probe on positive, see what our voltage drop is, and that's 1.064. which isn't a dead short and looks good. Now let's go the other way. And we get 0.601, which is what a reverse protection diode would be, like a Schottky diode. I don't see one on this side of the board. Now, we know that everything is shorted out. And the main culprit, as I said, are these burnt ICs right here. So, what are these ICs? Let's zoom in a little bit. I'll move this over so you can get a better look. There we go. Alright, so, actually zoom out a little bit. The output right here, these wires, they go to a pair of thermoelectric coolers that are underneath this plate that cools the pump laser diode here. And how they control that is they have all these DC to DC converters right here. So we have 6 DC to DC converters. These are the inductors, and they're probably buck, which means it steps down the voltage. TECs require a low amount of voltage at a high amount of current. And these chips are actually dual MOSFETs. So there's 2 N-channel MOSFETs. One of those MOSFETs are doing the switching to the inductor, and the other MOSFET is doing the rectification of the output. And we call this a synchronous rectification DC to DC converter. So all those need to get pulled out. Now we have a couple of other chips right here. These are all dual channel gate drive ICs. So on the other side of this board we have an ARM microprocessor, of which I believe controls these gate drive ICs. And what that does is it takes the signal from that microprocessor or whatever it's derived from, and it steps up the voltage and the current, so that way there's enough energy supplied to the MOSFET gates to make sure that they're fully on and conductive. So, my thoughts are that these need to be removed, obviously. I'm going to replace these gate drive ICs too, because if reverse power went through, most likely what happened would be is the 2 body diodes in the MOSFET shorted out to one another, either through the inductor or through the low resistance of the thermoelectric coolers, and, shorted out. So I'm concerned about any kind of backfeed of voltage, either from the inductors or whatever was plugged in incorrectly, also backfeeding into the gate drive ICs. So I don't know if they're good or not. I'm not going to risk it. I'm just going to pull those out. Now, given what we have, it looks like, let's see, 1, 2, 3, we have 3 TEC outputs, so only these two are connected, so these two could probably just actually go, and we only have to repair this section too, so that's a possibility. What else do we have? So we have this little module right here, and this is a DC to DC converter module. I'll move that over. So right here, and what this does is when the 12 volts, the voltage from the power supply comes in, you want to drop that power to a lower voltage because the pumping laser diode does not require that much voltage. Usually these have around 1.8 volts to about 2.2 volts maximum on them. And so it's high current. So this takes the voltage, steps it down to lower voltage, higher current. But the upside to doing this is you can also use a regulated, a linear regulator for the power supply, a linear regulating constant current circuit. And they got that here. So we have a couple of operational amplifiers, and on the bottom side we have a MOSFET, and then we have that current shunt resistor. Now I'm figuring it's going to be about 3 volts that it's going to come off this little DC to DC converter here, and probably at 40 amps, which is amazing that you can get 40 amps out of a little stick this size. It's really cool. And when the voltage is lower, that means you're not dropping as much voltage across the main regulating transistor. So for example, if you have, say, 12 volts coming in and you need 40 amps, here, that's 12 volts minus that 2 volts. So we'll say 10 volts times 40 amps. That's going to be, what, 200 watts dissipated on that transistor. Whereas if you drop it down to 3 volts, well, now there's only that 1 volt times that 40 amps or 40 watts being dissipated by that transistor. So the closer you get the voltage to your load, the less power heat is going to be generated by that transistor. Now, another thing to point out on the board is we got this right here. This is a 5 volt linear voltage regulator, and this will be supplying voltage to things like some of the DACs that are on the board, which I believe are these. This chip right here, which is I think a triple channel hex inverter, is a switch. And then some of the operational amplifiers like these up here. We've seen that on other laser drivers. That 5 volts is also most likely going to the ARM microprocessor on the other side of the board. So as long as we're getting the 5 volts from this linear voltage regulator, the majority of the like low-level signal side stuff should be fine. So that microprocessor should be fine. All the DACs and all the operational amplifiers should be fine. I am mostly concerned with the power rail generation. So what I've done is I've gotten the chip that controls this little DC to DC converter, and I have these chips as well. So I'll be replacing at least these. I don't know if this is good or not. We won't find out until I put power in, but this looks like it's fine. So once this is removed, we can check to see if we still have a short on these wires here. If not, we'll go ahead, probably remove the pump laser diode from here, check the voltage. It's going to be around 3 volts if it's operating correctly. And we can go ahead and see if the constant current circuit is operating. To give you an idea of what's on the other side of the board, and there's not much going on. I'm going to pull up the board real quick. Let's see if I have a convenient screwdriver laying around. We're doing a lot of stuff in the kitchen. Alright, I'm going to carefully rotate that. Okay, so here's the ARM microprocessor. This looks like it's it's an analog component of some sort. Probably another voltage regulator right here in the corner. And then we have, let's see what's that. That is a 3.3 volt regulator. And then we have these two components here. So this is the MOSFET that does the constant current regulation from that DC to DC converter. And then we got this part right here, which is the current shunt resistor. So as the voltage gets passed from the negative rail through this resistor, there's a little bit of voltage that's generated, and that's compared to a voltage reference somewhere on the board as it goes out through this N channel MOSFET right here. So pretty much everything on this board can be easily replaced except for that ARM microprocessor, because I'm betting that there's some sort of special software that's programmed on there. That's my thought. So I'm gonna get this back in position, and I'm gonna work on removing those dual MOSFETs right here on the top, because those have to go before anything else can be done. Let's see if they're marked. Not at all. Okay, so pin 1 here is in the bottom corner, right? So we can mark that down. Now, it's the shivery biscuit in my shop. Outside temperature is like in the negative, and that's in Fahrenheit. So today is a good day to use a heat gun to do some pre-warming, at least on the board. And we'll go with that. Alright, that should be all of those bad MOSFETs now removed. And I am betting that the short on the input here is going to be cleared. Let's go ahead and see. Yep, okay, so I'm reading about 160-ish K. Let's see, go on diode check. Yep, that's the right way. Yep, looks like a reverse protection diode, possibly 0.574. So it looks good. All right. Next step. Let's go ahead and remove the pump laser diode on the negative side, because that is the side that it's regulated on. And for the time being, I'm just going to solder that right onto the positive wire. That way it's protected from ESD. Beautiful. Okay, awesome. Alright, I'll need a voltage. 12 volts. We'll start at, say, 10-ish. Because all I want to see is if this DC to DC converter works and if I'm getting 5 volts out of the regulator. Let's check what my current input limiter is. I have it set to, let's say, set it to 2 amps for now. We won't be powering anything on the board that's high current right now. All I'm going to be doing is checking to see if there's a 5 volt rail, and then checking to see if there's the voltage from this DC to DC converter. That's it. As long as these aren't connected, nothing's going to be going to the TECs, and as long as the pump diode is disconnected, nothing is going to be going to the pump diode. So we'll be fine. Oh, I should probably connect. Give me a minute to set up here. Okay, now I'm set up to do the power rail test. So let's go ahead and do that, see what happens. I'm going to switch it on and see if it does something or draws a bunch of current. Okay, it's not drawing a bunch of current. We got a light here. That's a good sign. At least we know that LED is working. So let's go ahead and test the voltage rails. Right now I'm suspecting that the 5-volt rail is working just fine. So that should be ground, this should be output. 4.27, that's backwards. Oh yeah, I know, I'm not giving it enough voltage. Okay, well that's fine. Alright, and now I want to see what's at the output of the DC to DC converter. Now to do that, I'm going to put the positive probe on the positive output section of where the laser diode is connected. Wrong one. Because that is going to be the common positive, and the rail is going to be switched on the negative. And I want to check that at the input of the MOSFET. So it's going to be one of these two. We're going to see that voltage. So it says -9. That's strange. -9. I don't like seeing -9. Okay, so I went ahead and spent some time looking over the driver board, and I have learned a few things. So I want to start off by turning on the driver, and I have about 9 volts going into it. So to show you that, I am going to connect my meter probe to the input. So you see that 9 volts. So I went ahead and I wanted to see what was coming off the MOSFET. And to do that, I went and I have my positive probe on the positive input, because we're using an N-channel MOSFET to regulate. And if I put the negative probe on the source pin right here, you can see we get about 9 volts. That makes sense. But then it got really confusing, because when I went between the positive that's coming into the driver and the positive that's connected to the laser diode, I would expect them to be joined together, once again, because we're regulating on the negative side. However, if I put the meter across those, we get about 9 volts. So that's interesting, but it does mean that the DC to DC converter here is doing something. But it gets stranger. So once again, I have 9 volts going into the driver, and what I'm going to do is I'm going to turn up the voltage going into the driver with my adjustable power supply, and I'll bring it to the 12 volts that this driver normally operates at. Alright, and then I am going to go and see what voltage is now going into the MOSFET, which is 12 volts. So that got a little confusing, but remember, the positives aren't the same. So if I go and I put my positive probe on the positive that normally goes to the laser diode and touch the MOSFET source, now we got 7.7 volts. So there's something a little goofy with the voltage reference on this particular module. The voltage drops as more voltage goes in. That's a little strange. One of the concerning things is also, it seems like we're not properly constant current regulating. So here's what's going into the source, and then here's what's coming out of the drain, and it's the same voltage. Now, I thought the voltage was a little high, but when I went and looked up similar laser modules, I found out that those modules are kind of run in series. So the voltage is higher than I expected it to be for one junction, and the current will be lower. So far this is making more sense. Figure 5.5 to 6 volts, you get about 7 volts here. That means the voltage drop is about 1 to 1.5 volts at a lower current rating, say anywhere from 7 to 10 amps. That's only going to give us about 10 to 15 watts of thermal dissipation by that transistor. Now, I don't know if the laser is currently running at a point where it wants to operate in the threshold range. For some GPSS lasers, they will keep the pump diode operating at a certain point, so that way when you want the laser to turn on, it's already right there close to that turn on point. You don't have to worry about the material like the YAG crystal going to saturate and, you know, have a delay in output power. So that's pretty common. It could be a case that the constant current circuit has nothing loading it down and it's trying to put the diode into threshold and can't, so it's just turning on that transistor as much as it can. But it does look like that constant current circuit could be working. The DC-DC converter definitely working. If I look here on the section where we saw those MOSFETs blow up, we take this positive here, we can follow the trace down through this section right here, and it connects to the drain of that MOSFET. Now these are dual N channel MOSFETs, so that means that they're using that MOSFET on that side in reverse conduction, and when it's on, positive goes through. On this side, it uses the negative and runs the MOSFET as it's normally used, so the input voltage comes from this pin right here. And if we think about it, MOSFETs have the body diodes. They are conductive when you reverse bias them. So if we reverse bias them, both diodes are in reverse. So we get a negative current coming in through this pad, going through that diode on this MOSFET. We got a negative coming in from this side, going through that body diode. And they're going to meet, and they're going to short out and blow up, which is exactly what we saw. Now, I went ahead and I tested the pins on each one of these ICs, and the results were all over the board. Pun intended. And I don't like that. So I went ahead, I replaced these two ICs, and I think the next thing I want to do is put two new MOSFETs in. Looking at the configuration of these drivers, I think that two of these are needed to run one of the TECs, because if you take a look at this inductor here, we can see that the pad goes to positive. We take a look at this inductor here, you can see that it goes through to this fuse and then out to negative. So I'm assuming that a pair needs to be working in order to function. So that's the next step. Also got a green light here, which indicates that the microprocessor is doing something useful. So right now everything is looking good. Once the new MOSFETs are installed, what I expect to see happen is this base plate to cool down. If this section isn't working properly and there's a problem with it, there's a good chance that the MOSFETs are just gonna fry themselves again, but I'll cross that bridge when I get there. So that's the next step, the installation of new MOSFETs. Okay, at this point I now have those two MOSFETs installed, and I can go ahead and give it a test, and hopefully it works as it should. 3, 2, 1. That's good. No smoke. Let's go see if we have power coming off going to the TECs. It would be great if that was the case. Negative 1.2 volts. Well, there's something happening. Let's see if that cools down. That's warming up. Well, that would explain. I told you the shop is cold, but hey, warming up is something. Wait, 12 volts? 12 volts seems a little high. We'll see what happens. So far, no smoke. Oh, it's testing the wrong wires. Oops, that's why. Yeah, no, it's regulating. That DC-DC converter looks like it's working just fine. Cool. Well, one down, one to go. Two more gate drive ICs and MOSFETs have now been installed. Let's see if we have the same luck on DC to DC converter number 2. In 3, 2, 1, contact. Okay, we have a little bit of a voltage drop on the power supply. It's going to give me a little bit more current. The current drop, that's nice, so I'm assuming Then we're going to see about the same voltage on that second TEC. Now negative voltage. Yep, sure do. So that's about negative 9 volts. And this one right here, probably about the same. Yep, okay, so both of the TECs look to be regulating properly. Once again, I'm going to let this sit and make sure that it doesn't run away and get too warm, but it looks to be repaired. Alright, there's just a few things that I want to go over before I throw this laser driver back together. And the first thing is to make sure that the constant current circuit is being properly initiated by the microcontroller. So, to do that, I want to see how the voltage on the MOSFET gate responds versus the green light right here. I'm not concerned about the voltage as much as I'm concerned whether there is voltage or isn't voltage. So, to do that, I am going to take my 2 probes and I'm going to put my negative probe on the side where the source is connected. So that's right here, going down through this trace to this right here, and then onto this little test pad. On this side, on the far left, is going to be where the drain is, and I'm just going to take my positive probe, kind of stick that right here in the solder connected to that one resistor as carefully as I can. Alright, that should be good. Now, there's going to be a little green light here, and I don't want to see any voltage on here until that little green light turns on. So, 3, 2, 1. Alright, so barely any voltage. Now remember, there's no load on this circuit, so the voltage is going to swing up really high, and that's because there's no load going across that shunt resistor. So there's no voltage differential present on there, and therefore nothing to be compared against the voltage reference. Okay, 11.8 volts, that's good, and it came on when the light came on, so it looks like that's working properly. Next thing I want to check out is to make sure that there's no short going to the input signal wires, and a little concerning here because on the ground it's like there's some scorch marks, so just make sure that there's no short from there. So against ground in continuity, 80K, 86K, okay. So it doesn't look like it's shorted. Yeah, that looks fine. And then out of curiosity, I want to see what the voltage drop is across the actual laser diode. Now, remember, when I looked these up, they're in series, and there was only about a 1 volt drop across this, which is suspiciously low. I'm not sure exactly what the voltage drop is for the 1064 nanometer laser diodes, but I'm assuming that this is an 808 nanometer laser diode, so the voltage drop should be like 1.2 volts, so it's already a little low, and if that's in series, I expect that to be a lot higher. So to check that, I'm going to disconnect the laser diode. And I'm going to see what the voltage drop is in diode check without there being anything else connected. So, negative meter probe, and then positive meter probe. Okay, so it says over limit, which makes sense because I think my meter only goes up to like 2 volts, and the voltage drop of these junctions in series would exceed that, so that makes perfect sense to me. So I think I'm going to go ahead and reattach the laser diode wires and reattach these fan wires. We'll come back and see how it responds on the original power supply. Alright, it's now time for the final test. Now, it's not just a 10 watt DPSS laser, it's actually a pulse laser, and it can do pulses up to 54 kilowatts. I don't want to be in the same room with that laser. I don't have the proper eye protection, so it's set up in the other room. There's another camera in there that has the IR filter removed, and we'll take a look at that footage after the test. So I got the laser driver here, and I've got the client's power supply, and that's been checked. It does put out the 12 volts. For the TTL signal in, I have a lithium ion cell that's set up to a resistor network with a little switch that I can just tap. So that'll be the signal in, and it looks good to go. So let's go ahead and do it. So first thing is, got to plug in some power. One-handed, this is not easy. Okay, power is plugged in. Fans are going. We're gonna wait till that turns green. We're gonna give the button a little tap. We're gonna hope no smoke comes out of this apparatus, and hopefully all will be good. Alright, the light is green. We should be good to go. Testing. Alright, so the laser definitely burns things. It keeps a steady base plate temperature, and I still have both my eyes. So I consider this a repair well done. Now, I didn't get into how this laser works a lot in this video, simply because it's a client's laser and I can't really take it apart, especially in the laser head, because it's a pulse laser and I do not want to run any risk of contaminating those optics on the inside. Now, what I think is going on is we got a 808 nanometer pump laser diode here, and that 808 nanometer laser light goes through this yellow cable, which is a fiber optic cable, and that light exits the fiber on the inside of the laser head. Now, since it's a pulse laser, I think that we have a neodymium doped yttrium aluminum garnet, or ND YAG crystal on the inside of the laser, as well as some sort of passive Q switch. Now, I don't know much about Q switches and how they work. I don't have any, but basically what a Q switch is something that interrupts the resonator of the laser, and that way the crystal can continuously absorb the energy coming from the pump laser diode through the fiber optic cable, and at one point the Q switch will go transparent, or it'll stop interrupting the resonator optical pathway, and then all that energy that's stored in that crystal will avalanche and be released at once, and that's what gives us our pulses. Now, they're very short pulses coming out of the laser, but they're very powerful. I think it's 5.7 kilowatts, but we're talking on the order of like 7.5 nanoseconds. So the average power overall is only 10 watts. So interesting laser. First time looking at a pulse YAG laser for doing any kind of metal engraving and marking. I'd be interested to get into more of these lasers and maybe do a little bit more repair work on these. It was a fun experience, first time for me. So if you have a broken laser and you want it looked at, do give me a shout, contact me. Otherwise, I hope you enjoyed this video, and as always, stay tuned for more.